this week we're going to talk about sound waves. Sound waves are compressional modes, longitudinal waves, so they're different from transverse waves on a string, but they have many common features. So to make a wave propagate, what you need is a restoring force and some inertia in the medium. In the case of the wave on the string, it's the tension force that transmits the wave. And in the case of sound waves, it's really the pressure force. And the idea is that you will be compressing the medium, and the increase in pressure due to the compression will transmit a force and transmit the wave. Okay, let me show you an applet here that kind of describes, tries to simulate what a sound wave might look like. Okay. Now, one thing to point out, you can have a sound wave in any medium. It doesn't have to be a gas. It can be solid, can be liquid, can be a plasma, which is what I study. So all you need, again, is the ability to compress the medium and then have a restoring force that resists the compression. So, for example, if I take a balloon full of air and try to compress it with my fingers, it's hard to do that because there's a force pushing back, which is the pressure of the gas. And so as I compress it, the pressure gets bigger, and that results in the restoring force. Okay. So what I'm showing you here is a simulation. The yellow thing here moving back and forth is some physical object, a wall that's moving back and forth. It might be the membrane inside your speaker cone that vibrates and pushes air to drive the sound wave. And you imagine what it does is pushes on air molecules right next to the membrane and basically pushes them off to the right to start the wave. And then the white things here are meant to be air molecules. And what you see happening is you form a clump. So as you see this pushes, it forms a clump, and it looks like this clump just moves all the way to the right. Okay. Now in reality, what you're doing is forming a wave pattern. So the air itself is not moving to the right like that. That's a pattern in the air, a compression front. So to demonstrate that the air doesn't move, I've highlighted one of the air molecules, the yellow thing here. And what you see is that the air molecule is just moving backward and forward in place. And that's what all of these particles are doing. Now it appears like you've got one wavefront moving this way and then a backflow here, but in reality that's just an optical illusion by the way the particles, the wave pattern makes you think that's what's happening. Okay, but it's an important point that the particles move back and forth. Okay. And if we watch this particle, we see what happens when it encounters the compression. It gets pushed off to the right, okay? And when on one side of the compression, then it's pushed to the left when it's on the other side of the compression, okay? And that's the pressure force acting. So the pressure is maximum at the compression, and it decreases away. And it turns out that it's the gradient in the pressure, the change in the pressure that drives the motion of the particle. So let's talk more about that. So if I consider this membrane moving back and forth, again what it's doing is just moving, displacing a set of air molecules to the right. Okay, so we're going to define the displacement of the air molecule as a function of space and time. And that just measures how far the air molecule moved at a certain instant in time. So it used to be here, and it has moved to here. So we define the displacement to be, when I say x, what I mean is this location. And then d tells me how far the particle has moved away from where it used to be. Okay, so that's kind of a funny concept. It's not measuring the position of the particle. It's measuring the distance that the particle that used to be at the position x has moved. Now, because we know that these particles just vibrate back and forth, this is a valid concept because there's a certain location associated with each particle. It's, you can imagine it's sitting, in this location here. This is its equilibrium location, and then it just moves back and forth. So D describes where the particle is relative to where its equilibrium point is at any point in time. Okay, that's what that means. All right, but okay, so I'm displacing these particles to the right. What that does is, so let's imagine the very beginning. So I just start to push. So the gas that's over in this region has no idea what's going on. The only particles that know anything are the particles right here. Okay, and those particles get pushed to the right. And so the particles over in this region haven't moved yet. And what you do is you end up building up the density because you've pushed additional particles from this region here, okay, over to here. Okay, and so the density goes up, and therefore the pressure goes up, and that gives rise to the restoring force. Okay, so you imagine the pressure is now high right here, it's low out here, and where basically the pressure force acts to push particles from regions of high pressure to regions of low pressure. And so you have an effective force that pushes particles this way and that way. And then it's as if you've moved the membrane to this location, and now the pressure compression area is acting as the membrane and pushing particles further to the right, and you end up building a new compression over here, and then the process continues and the wave will propagate. Okay. All right. So now I should say a few words about the pressure force, okay, because it's actually a special, it's not a real force on air molecules inside the gas, okay. Now you can think about the pressure force on a balloon, okay. So the reason a balloon stays inflated is because the air molecules inside push against it. So there is a real collisional force between the air and the membrane. So the pressure of the gas is transmitted to the membrane via collision. But within the gas, you don't need collisions to transmit the force. It turns out that pressure forces aren't really a force on particles. It's a statistical effect. And let me try to explain that now. So if you look inside a gas with a temperature, so I have a bunch of particles inside a gas. To say something has a temperature or something is hot indicates that the particles inside are moving around. They're not moving together, so it's not as if there's a wind in the air, so that everything's moving together. What having a temperature means is that you have random kinetic energy. So each particle has a certain amount of kinetic energy, but there's no particular orientation to the velocity. And so you have particles kind of moving in all directions. And so there's energy in the gas, but it's not energy in the net motion of the gas. Everything on average is sitting still in the air. But there's energy locked in the random motion of the particles. Okay. So if I look at a uniform gas, so the same amount of gas, same temperature of gas is everywhere, and I draw an imaginary line, there's the same number of particles going this way as there are going this way due to random processes. Again, the particles are going in all directions, but if you pick out the particles that cross the boundary, there's equal numbers on average going one way versus the other. Okay. However, if I imagine a situation where the gas is non-uniform, okay, so I imagine a situation where there's a clump. Okay, so let's imagine analogous to our sound wave. In this region, there's a lot of particles. So somehow we've compressed a region in space. So here the pressure is higher. Okay, and over here the pressure is lower. So if I look at the boundary between these two regions, again, these particles to the left of this boundary are moving randomly in all directions, but some of them are going across the boundary. And there's some rate at which particles go this way. Now, in a normal gas that's uniform, that would be completely balanced by particles coming back the other way. But now in this case, I have fewer particles coming back. So the net result is that I get a flow of particles, and really a flow of momentum. That's what makes it a force. I get a flow of particles that goes down the pressure gradient. Okay, and that it acts as an effective force, and it turns out you can write the force as minus dp dx. Okay, that's the force that is effectively, this is a force density. I should be very clear about that. This is the force per unit volume. Okay, on the particles. But again, it's not really a force. You're not really pushing. The particle that happens to be sitting right here is not getting pushed by being at the region of the pressure gradient. So my explanation during the applet is not quite right. Okay, in fact, the applet's not quite right because it doesn't really show you the random motion of the particles. Okay, so the particle sitting here doesn't really get pushed. What happens is particles that are nearby will flow through that point. Okay, and it looks as if you're pushing particles to the right, but they're moving on their own accord. They have energy already, and they're moving to the right already. They're just not canceled out by particles moving to the left. Okay, that's a tricky concept, and we'll come back to it when we talk about thermodynamics. Okay, oops, there we go. All right. Now let me just talk a little bit more about the pattern of a sound wave, and in the next video I'll do a derivation of the wave equation. But we imagine that our sound wave is a displacement function. So particles in the air are moved left and right by in the sound wave. And so we can write a displacement function that looks like this. Okay. So all the particles that are in this region here have displacements that are positive. That means they're being pushed to the right. Okay. All particles that are in this region here have a negative displacement. That means they're being pushed to the left. So you can see I have a point of accumulation. So at this location, I'm going to get a clump of density. This is going to be an enhanced density or a compression. Okay, compression, I'll just do that. However, if I look just to the right here, I have a situation where these particles here are also moving to the right, but the particles below here are moving to the left. And so at this location, I have a rarefaction. I'm losing particles here. So this is a rarefaction, as it's called. Okay. And so the pressure here in this region goes down, okay, relative to the ambient pressure. The pressure here goes up, okay. So if I look at the pattern of the pressure, let's see, there we go. What I have is the following. Okay, I have a situation where in this region here, I get an enhancement of the pressure over the background pressure. Okay, and then in this region here, I have a reduction in the pressure. So what I'm plotting is the pressure due to the wave. So this is not the total pressure. The air pressure always stays positive, but this is the perturbation of the pressure due to the wave. Okay. All right. And so if I continued it correctly, this would be another rarefaction here. And let's see, did I get this side right? Yeah, that looks good. Okay. All right, so this is a little bit funky here. But anyway, I get pressure enhancement here, pressure depletion here. So the forces will tend to be on the pressure gradient. So I'm going to push downhill in pressure. So the particles will be pushed that way and that way in the wave. Okay. So the relationship between displacement and pressure is that they're out of phase for the argument that I just gave you. Okay, so I'll do a derivation of the wave equation in the next video.